Okay. Hello, everyone. Today I will present you our work, ViDoRAG. This work aims at improve the performance of visually rich document in a RAG system. So I will first give a brief introduction of our work, including the VidoSeq dataset and the VidoRAG framework. Then we will take a detailed look into our framework, including the multimodal hybrid retrieval and multi-agent generation. And finally, we will have a look at the experimental results of our VidoRAG framework on the VidoSeq dataset. And last, we will talk about our future work. So first, our work aims at improve the performance on visually rich document. So traditional RAG methods face challenges in understanding visually rich document. In this sentence, we can find two key elements. One is traditional RAG methods, and the second is visually rich document. So I will explain it step by step. First, what is the traditional RAG methods? It is proposed by OpenAI. It is used to add external knowledge to large language models. For example, if I had some knowledge that is stored in some document, we will first transform the document, the knowledge in the document into text. Then we will split the text into small chunks and using an embedding model to transfer these chunks into vector. And then we can use a vector database to store all these informations. Then when we want to use these informations, we can transform the query of the client into a vector and search it in the vector database. And we can get the most relevant information from our database by using the similarity between vectors. In the OpenAI's best practice, it uses the top 10 chunks and it adds these chunks into prompt to improve the final performance of the large language models. Okay, that's the traditional RAG methods. And what is visually rich document? We can say that I give an example here. It is also a page from a document in the real industrial scenarios. If I pose a question, what is the competition media in East? So how can we answer these questions? We have to first find out the color of competition medias. That is the purple. Then we know that the purple is in this column. Then we have to find out where is the East. Okay, East is here. So we can find that the answer is 6%. So imagine that if we use the traditional RAG, how can we deal with that? We have to first transform this document into text. But how can we transform these colors? No, if we use the OCR-based methods, we will lose all these colors. So we cannot find out what is the color stand by competition medias. So we cannot respond these questions. So that's the difficulty and the challenge the traditional RAG methods face. So we propose our work, ViDoRAG, to tackle these challenges. So to deal with these problems, we have to build a benchmark to evaluating the performance of RAG in these scenarios. So we try to reuse the traditional VQA dataset, but we find that in the traditional VQA dataset, it is not suitable for RAG system. for example, if we have a query, we find out that in the traditional VQA dataset, we can have many answers referred to this question. It is not suitable for a RAG system. So we introduce a ViDoSeq dataset to benchmark this task, and we propose a ViDoRAG framework to bridge the gap. First, our ViDoSeq dataset is released in the GitHub, and all of you can use that. It is designed for the visually rich document, and it contains 1,200 questions across a wide area of domain. And each query has a unique answer. It's very important in a RAG system to have the unique answer. And we have diverse content types like text, chart, table, and layout. And we have multiple reasoning types like single hop and multi-hop. And this is a pipeline we built this data set, including data collection, query creation, and we manually reviewed the answer, and we finally use some automatic methods to refine the answers. So we have a high quality. So this dataset has a high quality, and I recommend you to use this dataset if you have the same problems in your situation. And now we have the benchmark. We can evaluate our RAG systems. And after the evaluating, we find that the traditional RAG systems has two main drawbacks in this situation. One is the inefficient retrieval performance. The second is the insufficient reasoning capabilities during the generations. So we propose two methods. One is for retrieval, and one is for generating. First, for the retrieval, we can see that this visually rich document, it contains many visually elements. So if we convert it only to text, it will lose many information. So in our work, we use also we also use the image, the raw image, and we use a multimodal embedding to embedding this image. So in the retrieval phase, we have two pipelines of retrieval. One is using text embedding to retrieval by text information. The second is to use multimodal embedding to retrieval from document images. We take the page, we take the whole page as images. Yeah, so once we have the two pipeline results, we have to merge that. Yeah, so we propose sophisticated strategies to combine them together. If you are interested, you can see our papers. It is also on archive. Yeah. After that, in the generation steps, we find that if we use a visually language model in the RAG generation stage, we have another problem that doesn't occur in traditional RAG systems that use only language models. That is the visual language model cannot deal with too many images. For example, since nowadays the language models have larger and larger input lengths, so the language model can take, for example, 100 pages as input. But if we use visual language models, we can't take 100 images as the input of a visual language model. So we have to compress these images. For example, we compress 9 images into one. Yeah, that's so we can give more information to the large language, to the visual language models. But if we compress the image, we can lose some information. For example, some some section of the image is blurred, the model cannot see it clearly. Yeah, that's why we propose multi-agent generation with iterative reasoning. The iterative stands that if the model think some portion of the image, since we compress them, some portion of the image is not clear, but it is very important to answer the questions. It can zoom in this section and examine it detailedly and get the answer, and then zoom out and see if there are other sections important, and it can zoom in and zoom out. Donc, after the iterative process between seeker agent and inspector agent, once the inspector agent think it has enough information, it can generate a draft answer, and finally an answer agent can generate the final answer. Yeah. I think it's very important for zoom in, zoom out action. Like in these days, other companies have also released the visual language model that can turn or zoom in, zoom out some images. I think it's a very important action in the visual language model. Okay. So let's take a look at the final results. We find that we use accuracy and recall as our evaluation matrix, and we compare our ViDoRAG to TextRAG and VisualRAG. And the results shows that our ViDoRAG outperforms the existing methods by around 10% improvement. Yeah, that's a great improvement. And we can see that we use by using the retrieval strategies, we can we can achieve the comparable performance by reducing the candidate pages from 10 to 6. Yeah. And our strategies, since it is an iterative strategy, so it takes more time. It takes around 2 times slower than traditional RAG. So, but it improves the overall performance. So our future work will focus on optimizing the framework's efficiency while maintaining the high accuracy. And we are also doing some reinforcement learning trial on this process. And I think the point is that the ViDoRAG demonstrates that there are significant improvements in visually rich document if we use a multimodal embedding and visually rich and a visual language model in this situation. Yeah, and that's all for my presentation. Thank you.